Today we're doing a complete scientific autopsy on the birth of our universe. We usually think of the Big Bang as the absolute beginning of everything. But there's this incredible, surprising secret hidden right in the physics. The standard Big Bang theory doesn't actually explain the bang itself.
Welcome to our channel, where we explore the darkest corners of the cosmos, the mysteries, the threats, the unknown. This is space like you've never seen it before.
So, what actually banged in the Big Bang? It sounds like a joke, right? But the standard scientific model is technically a bangless theory. To figure this out, we have to look past the cooling aftermath of the explosion and trace things all the way back to the very spark that ignited the whole shebang. Let's break this down by comparing two distinct ideas. First, you have the standard Big Bang. Really, just think of this as a theory of the aftermath, how things cooled down and evolved. But then, we have cosmic inflation. This is what physicists basically consider the Hollywood prequel to the Big Bang. It's the theory that actually gives us the propulsion, the true engine behind the bang itself. Now, we actually know a lot about that aftermath. Thanks to insanely precise measurements from the Planck satellite, we can say with total confidence that our local universe has been expanding for exactly 13.82 billion years. But if we're doing a true scientific autopsy here, we can't just stop at billions of years. To understand the actual beginning, we have to rewind to microscopic fractions of a single second. And that brings us to cosmic inflation. This is our prequel. It's the period where a microscopic patch of space underwent an extreme, explosive, literally exponential expansion. We are talking about a true miracle of physics that basically set everything into motion. Now, this completely flips our basic assumptions upside down. We normally think of gravity as a strictly attractive force, right? Things pull together. But Einstein's equations of general relativity actually allow for negative pressures. And under extreme conditions, this negative pressure literally turns gravity on its head, making it act as a massively powerful repulsive force. Let's map out how fast this actually happens. At 10 to the minus 37 seconds, this inflationary expansion kicks off, and just a blink of an eye later, by 10 to the minus 35 seconds, after something like 100 doublings in size, the exponential expansion is already over. In that unimaginably tiny window, a subatomic patch of space inflated to roughly the size of a marble, creating the hot soup of the Big Bang right at the 1 second mark. But wait, you might be wondering, how on earth can the universe expand exponentially, multiplying its volume so massively while maintaining a constant energy density? Doesn't creating all that energy out of literally nowhere violate the most sacred foundational laws of physics? Actually, not at all. It perfectly illustrates the ultimate zero-sum accounting of our universe. The massive positive energy of matter and radiation is perfectly, exactly canceled out by the negative energy of the gravitational field filling that space. So, as the universe expands, the positive and negative energies just grow together. But the total energy, it remains exactly zero. Okay, having set the stage, let's look at how inflation acts as the ultimate cosmic detective for our scientific autopsy. The classical Big Bang is a fantastic theory, but it leaves us with three massive, glaring mysteries that it just can't explain on its own: the homogeneity problem, the flatness problem, and the magnetic monopole problem. First up in the autopsy, Mystery 1, the homogeneity problem. When we measure the cosmic microwave background, it is incredibly uniform in all directions, down to an accuracy of 1 part in 100,000. But how could opposite ends of the universe reach the exact same temperature if they were expanding way too fast to ever communicate or transfer heat? Think of air filling a room to equalize perfectly. Without inflation, this equilibrium is literally impossible. But inflation tells us the universe started out microscopic, tiny enough to easily reach a uniform equilibrium, before it was rapidly stretched into the massive, uniform universe we see today. Next up, Mystery 2, the flatness problem. This deals with the precise geometric balance of the universe's mass density compared to its expansion rate, which cosmologists call omega. In the standard model, omega equaling exactly 1 is an incredibly unstable equilibrium. Without inflation, omega would have needed to be tuned to exactly 1 to an astonishing accuracy of 15 decimal places just 1 second after the Big Bang. That is exactly like trying to perfectly balance a pencil on its tip for 14 billion years without it ever falling over. And this is exactly where our cosmic prequel swoops in to save the day. Inflation's repulsive gravity acts so powerfully that it flattens out the universe's geometry, forcefully driving omega towards exactly 1 exponentially fast. It completely eliminates the need for some impossibly perfect initial balance. What's wild is that this theoretical prediction was beautifully confirmed by astronomers back in 1998 with the discovery of dark energy. Dark energy is this mysterious material with negative pressure that fills space, causing the current expansion of the universe to accelerate. And it perfectly balances our modern energy budget to make omega exactly 1 today. Moving on to our third mystery in this autopsy, magnetic monopoles. Grand unified theories, the ones that merge the fundamental forces of physics at extreme energies, predict that the early universe should have produced an absolute swarm of massive, heavy particles called magnetic monopoles. Yet we don't see any, anywhere. While the standard Big Bang really struggles with this overabundance, cosmic inflation solves it beautifully. That explosive expansion simply took whatever monopoles existed and diluted them down to completely undetectable levels across the vastness of space. But that brings us to the seeds of the universe. Here's a critical question. If inflation acts like a giant cosmic iron, making space perfectly smooth and flat, where did all the lumps, the galaxies, the stars, our Earth actually come from? Well, we have to look at quantum mechanics. The uncertainty principle dictates that absolutely nothing can be perfectly uniform. So microscopic quantum fluctuations were essentially frozen and stretched to macroscopic sizes during inflation's rapid expansion. Those tiny quantum ripples literally became the seeds for all the massive cosmic structures we see today. Finally, completing this scientific autopsy leads us to the most mind-bending implication of the entire inflationary model: the multiverse reality. This is driven by eternal inflation. Here is how it works. The repulsive gravity material that drives inflation decays randomly with a half-life, a lot like radioactive decay. But because the exponential expansion so easily outpaces this decay, inflation never completely ends everywhere at once. It constantly forms new, isolated pocket universes wherever the decay happens, while the remaining material just continues to inflate eternally. Which leaves us with a truly provocative thought to end on. Is our 13.8 billion-year-old Big Bang just one tiny pocket in a never-ending multiverse? What if our entire known universe is really just one single magnificent bubble in an infinitely expanding cosmic landscape? It completely reframes our place in reality, doesn't it? Thanks for joining me for this explainer, and as always, keep questioning the cosmos.
If this video made you think, hit like, share it, and subscribe to this channel. Because the next mystery is even deeper. Until then, stay curious and keep looking up.